I'm going to ask somebody for their sample data. Somebody want to tell me what their displacement they calculated was? Somebody want to share? 7 minus 0 equals 7 meters as the displacement. How many of you had 7 meters for your displacement as well? Make sure you are thinking about the equation for displacement, that it's final minus initial positions. Somebody want to tell me what their average time for, if they had 7 meters, what was the average time that you got? L? 2.935 seconds, 2.94 seconds. I'm going to go ahead and round this to 3.0. Actually, no, I'll leave it at 2.9. Let's just leave it to the 10th of a second.
You all write 2.9?
No, you write what you had for your average. So next we're doing the velocity.
Are you recording that?
Yes, I'm recording this. What's going on the document camera? Well, you're not in the movie, Pat, other than your voice. This is our new version of the velocity equation, which is displacement divided by the time. What was our displacement? 7 meters. What was our change in time? 2.9 seconds. I do that on my calculator. 7 divided by 2.9 equals 2.4 meters per second. You might get a slightly different velocity if you have a different time or if you used a different displacement. Next, it says make quantitatively accurate. What does quantitatively accurate mean? It means with numbers. It's not general trends, steeper, shallower, horizontal for constant velocity. These are with the real numbers. So I'm going to put time on my x-axis, and I'm going to put position in meters on the y-axis, and then I'm going to scale my graph. In terms of time, 0. Let's go ahead. I'm going to go by 3 Z's. 1, 2, 3. Does that work out? That does work out fine. You can go by 4 Z's if you want. You can scale yours any way you want. Just try to use as much of the graph as possible. In terms of positions, it's best probably to go, each box is 1 meter. Now, how can I make a quantitatively accurate position time graph? Do you know your starting position? At time 0, where were you? 0. Do you know your ending position? At time 2.9 seconds, where were you? Or where was he? 2.9 seconds, he was at about 7. And then you can connect those 2 dots. Please use a straight edge of some sort, and you can assume that he continued on at that same velocity for another couple hundredths of a second. So you can continue your line all the way out. I'm going to start setting up the velocity time graph. And use the same scaling that you did for time on your velocity time graph. Zero velocity is right in the middle. And since I calculated the velocity, my velocity would be 2.4, you calculate what your velocity was. And I'm going to draw a line horizontal at 2.4. Thank you. And I'm going to just use a colored pencil over it because it's kind of hard to see what the line was. That looks even worse because now it looks like it goes all the way up to 2.5. But that line is really at 2.4. And we're going to assume that he continued on past 3 seconds because he was going at a constant speed, and he did continue past when you stopped timing. It says to mark the initial and final positions on the graph. Well, you kind of already did that because those were the points that were used to determine your line. So, oops, that's not initial, that's final. This is the final position. This was my initial position. So at time 2.9 seconds, he was at 7 meters. At time 0, he was at 0 meters. If I was only given this graph and I didn't know any of the data points that went into this, I could determine his displacement from this graph. Displacement is the final minus the initial position. And what was his final position? According to the graph, it was 7. What was his initial position? 0. So the displacement was 7 meters. You will not always be given the points that go into this graph. I might just give you a position time graph and say what was the displacement between 0 and some seconds. I think students make this question out to be much more challenging than it really is. It's just reading the numbers off of the graph for position and taking the difference between the two. This question over here, though, this is all new, and you would not necessarily be able to figure this one out through your intuition. It says to graphically represent. Anytime you see those words, you are going to be doing some shading. You're going to shade it in. Shade what in? You're going to shade in a region of this graph. What region are you going to be shading in? Well, you're going to be shading in from the time that you started, time 0, from time 0 to 2.9 seconds. So we find 2.9 seconds, something like that. And I shade in from my 0 velocity line all the way up to the line of constant velocity that I drew. I will not grade you on your shading abilities. And we say that this shaded region, I'll wait till you're done shading because I see that you're all still shading. Hold on. But it only went to 2.9 seconds on my graph for my calculations. Yeah. So if you timed all the way to 3 seconds, then you're going to shade into 3. If you timed to 2.8 seconds, you're going to shade into 2.8. Even if you're still shading, stop what you're doing, look up here, because this is the big leap. They say that this shaded region represents the displacement. What is the shape of this shaded region?
Rectangle.
A rectangle. What is the formula for the area of a rectangle?
Height times width.
Length times width. Now, look up here. This is the big leap. So we're saying that this area here is the displacement. The area is the displacement. Well, what are the two dimensions for length and width? Or length and width? What are the two dimensions that we have on our graph? Jack?
Time and velocity.
Time and velocity. Or I can just write velocity times time. This shaded region represents the displacement or the velocity times the time. Have you ever seen this equation before? Delta x equals velocity times time? Yes, we looked at it earlier in the period. So if I want to know about the displacement, I take my velocity, which was 2.4 meters per second, and I multiply it by the length of time that he traveled for, 2.9 seconds, and I multiply those two numbers out, 2.4 times 2.9 equals, and I get 6.96 meters. Why didn't I get the same exact displacements from both methods? Why didn't I get the same exact displacement? Dexter?
Because you might not have stopped at exactly 7 meters.
I might not have stopped at exactly 2.9 seconds. Did I round my velocity? Did I round my time? Yes. So in theory, these two answers should be the same. And if they're not the same or pretty darn close, it's because of rounding errors. But they should be pretty close to the same answer. Same displacement, two different methods.